3, and we start with chapter 3 with exponential functions, which is something that we did do in Algebra 2 last year, and then we get into logarithmic functions, and really we're going to get into a lot of the applications of this a lot more than we did last year. We did a little bit of that last year in Algebra 2. We talked about exponential growth and decay and radioactive decay, but we're going to get into the finance of it a lot more. There's Logan, are you ready to go here? Then stop talking. You don't have to move your mouth to do it. Stop talking. If it helps, put those in your mouth. Maybe that will help. At the end of this chapter, we're going to get into formulas for figuring interest rate with savings account, interest rate with loans, stuff like that. You won't be figuring that in your future, but that's how people figure out mortgage rates and all that stuff. Is there are rules and there are formulas, and logarithms play a big part of that. So these really do have a lot of applications. So let's just jump in here. Well, we should have been talking. Because you never stop talking, and it's rude. No. We're going to spend a couple days on this section. Today we're just going to kind of talk about what is an exponential function, how do I graph an exponential function, and then tomorrow we'll get into more of the applications of it, of what does this apply to, and definitely biology, population models, we can use exponential functions. Here's a nice little vocab word for you, transcendental functions. Oh look, I tried to write that over there under PreCalculus today because we were doing derivatives of transcendental functions, but I forgot my S. Transcendental. I just put Good thing no one else knows how to spell that word. A transcendental function or a transcendental number is just something that doesn't really work out so nice. And if you remember these from last year, they're not that great of numbers to deal with sometimes, especially ln, if you remember that, and e. Those are decimals that are like pi. They don't really work out so nice. These are not polynomial functions. They're not nice and smooth. They definitely have their own little category when we're talking about them. So I just wanted to throw that word in there for you. But let's get to the good stuff here. What is an exponential function? I'll let you write down, then we'll kind of go through it. But hopefully this is kind of like, oh yeah, I kind of remember this. In the last chapter, we talked about power functions. We talked about x to some power. Remember that an exponential function is when the x is up there in the exponent. That's what makes it exponential. So my exponent doesn't look very high here, but our equation that we're going to use here is f of x equals a times b to the x power. It's kind of like our go-to formula for an exponential function. And there's all these rules for exponential functions on what a and b and x are allowed to be. And so that's what a lot of this says. A is not allowed to be 0, and that should make sense to you, because if a was 0, then the whole thing would be 0, and that's not an exponential function. B is positive. We're going to talk about this a little more tomorrow. What happens if b is not positive? What does that change to? But in our examples today, b should be positive number, but not equal to 1. And again, think about it. If b was 1 to the x power, is that ever going to change no matter what x is? No, so that would also not be an exponential function, because 1 to any power is still just 1. And x can be any real number. So x can be irrational, it can be rational, it just can't be imaginary. One of the first things we're going to do is write some equations for exponential functions, and it's really important to pay attention to this next part here. The a is always your initial value. That means where you start. That's another way of saying when x is 0, a is what you get. That's the initial value. And b is your base, and we're going to see what happens as the base changes. Okay, so that's kind of a lot of words there, but that's kind of some important stuff here. So the first thing we're going to do here is we're just going to practice evaluating exponential functions. When we have a test or a quiz in this chapter, sometimes I'm not going to let you use a calculator, but even if I do let you use a calculator, this is the chapter that I'm going to be picky on what calculator you're allowed to use. There are some calculators that have math print or pretty print, that's what math teachers call it, but it means they give you really nice answers for logarithms and exponential functions. And then there are the calculators like I have, that if you type 3 to the negative 2 power on it, it's going to give you a decimal. I want you to be able to do that without needing a calculator. So if you type in 3 to the negative 2 on your calculator and it gives you a nice answer, not a decimal, you're not going to be allowed to use your calculator on the test. And so I will be checking that. If you have a question about that and you want to know now, I can look at your calculator later. But this is one of the chapters that I will limit your calculator use. Like you would just use one of mine. I will. It's not that many. Or maybe we'll just have part of the test with the calculator and part without. Also, next semester, when we do trig, calculator, I'm going to limit those calculators that give you really nice answers, because there are certain trig things that you need to know, and there are certain calculators that give you those answers. And so those calculators are really nice. I like them. But in pre-calculus, when I'm testing that, you're not going to be able to use those because you're going to get answers. Well, there's lots of different ones that give them to you. But I think Kimberly has one, right? You have one that did that nice one? And I don't know. There's lots of people in here that have them. I see them every time I go around and check. Justin Barry has one. Natural display, Casio natural display, that's one of them. There's a Texas Instrument one. But you know, if you type stuff in and you always get really nice answers, you always get lovely worked out fractions, and you don't have to hit a fraction button, there's a good chance that that's your calculator that I'm talking about. So we'll deal with that later. But like on this one, I want you to know how to do with this without a calculator. If I plug negative 2 in here, then I'm going to get f of negative 2 equals 3 to the negative 2 power. What does that mean? What does a negative exponent mean? It means a fraction. It means move it to the bottom. So that means 1 over 3 squared, which would be 1 over 9, right? There are some times that you will get to use a calculator, and there's some problems today that say use a calculator, like this one. Evaluate to the nearest thousandth. That means if it doesn't work out to something that you could do nicely, I do want you to use your calculator. When we get to the story problems in these sections, most of the time we're not going to get nice answers, and it's really important that you're able to use your calculator correctly. On this one, if I did 3 to the negative 4/9 power, I could move it to the bottom, and I could say I'm taking the 9th root of 3 to the 4th, but that's not something I could do without a calculator. That is 3 to the negative x. So this is one that I do want you to type in your calculator, because it's important that you're able to use your calculator correctly. How do you type an exponent like that? What button do you use? The caret button. That's how my calculators are. Other ones might have different numbers. But you're going to hit the caret button. Here's where it's really important. On my calculators, at least, you have to say that whole negative 4/9 is to the power. If you just type 3 caret negative 4 divided by 9, you're not going to get the right answer, because your calculator is going to take it to the negative 4, and then it's going to divide the whole thing by 9. So you have to make sure that you put that exponent in parentheses. If you don't, then you're not going to get the right answer. So make sure that you're practicing these. There's some on your homework that are just practicing using your calculator. If you don't use your calculator right, you're going to get wrong answers. So let's make sure we get the right answer here. 4 divided by 9. If we round to the nearest thousandth, how many decimal places is that? 3. Tenths, hundredths, thousandths. Sometimes people think that's 4 for some reason, but make sure you know that that's only 3 decimal places. That would be 0.614 if we're rounding to the nearest thousandths. Yes? Did you get that? What? You use the fraction button, and what did it say? Error? Did it give you a fraction?
Like 3 -1.
So you use fraction instead of division sign?
Yeah.
And you got the same answer?
Yeah.
Okay. That's good. Because a fraction sign is really just a division sign, right?
Yeah, but
And then you didn't put a parenthesis. That makes sense. There you go. I wasn't following you. Justin says if you use the fraction button, then you don't have to put parentheses because it wants the other part of the fraction. I'm with you now. That's good, right? We can do that. How about this? There's one like this on your homework, and there's probably a good chance you're going to see one like this on a quiz or a test. Just like when we did linear equations, I can give you a couple points and I can ask you to write a linear equation. When we did quadratic equations, I could give you a vertex and a point, and you could write the equation. It's the same thing for exponential functions. If I give you a bunch of points, actually you don't even need all these points, but you should be able to use the formula and use what we know to write the equation for that. And I wanted to do this one because people always struggle with it at first. It says determine a formula. That just means write an equation. I just wrote it how the book wrote it. And I think in the book they actually give you like an XY chart, but that's exactly what I've given you here. I just wrote it out in ordered pairs. So they're telling us we want an exponential function that goes through these points. -2, 108, -1, 36, 0, 12, 1, 4, and 2, 4/3. Sometimes it might be something you can just figure out, but I want to show you very easily how you can do this algebraically every time. Just like with a linear equation, we have a formula, y equals mx plus b, and we know that that's our formula. We got to find m, we got to find b. Quadratic, we have y equals a times x minus h squared plus k. We have to find h and k, and we have to find what a is every time. For an exponential function, we have a formula. Go back one second. Right here, this is your formula that you're trying to write. F of x equals a times b to the x power. So when it says write an exponential function, I'm going to write y, but f of x and y are the same thing. A times b to the x power. Linear equation, we can just find slope. We can subtract, we get slope, and we can plug in a point. Quadratic, they always give us a vertex, so right away it was h and k that you can plug in. For this one, you're always looking for what's the easiest one to find first, and for me, that's the initial value. The initial value is a, and the initial value is where you start, which means what do you get when x equals 0? So when x equals 0, do we know what y equals in this example? Can they tell us? 0, 12? I think so. For now. There might be some we have to do a little more work on later on. And I just want to show you what happens if we plug in 0 for x and 12 for y. I want to show you what happens, but then maybe you're going to be able to come up with how can I find a without actually doing the work every time. If I plug in 12 for y and 0 for x, I would be left with the equation 12 equals a times b to the 0. Do you agree with that? What does anything to the 0 power equal? 1, which means this is just 1. So do you agree that that means that a has to equal 12? Every time, your initial value will be whatever that, when x is 0, whatever this is, will be your initial value, or your a value. If you forget that, you could just plug it in and solve it. And so now we have a equals 12, so now I have y equals 12 times b to the x. Think about with slope, once we have slope, we still have to find b, so we have to plug in another point. That's what I have to do here. Logan said we could plug all of them in. We just need to plug one of them in. No matter what we plug in, these are all going on the same equation. You can pick any of these numbers, and when you plug it in, have to do a little algebra, but we should be able to solve for b. It really doesn't matter which one we plug in, I guess. I think 1 and 4 look pretty good, but it really you're gonna get the same answer either way. But if I plug 1 and 4 in here for x and y, I get that 4 equals 12 times, oh, that works out really well because that's just b to the first power. If you plugged in something else, you're going to have to do a little work to solve that, and that does get a little bit harder. That's really easy to solve for. What is b going to equal? Or how would I solve for b? Divide by 12. Lots of people get in a hurry here, and lots of people are going to say b equals 3, and they're going to get the wrong answer. Because really, b equals 1/3. Which means our base is 1/3. And just like linear and quadratic, you got to write the equation. So our answer is y equals, or f of x equals 12 times 1/3 to the x power. And I like to put that 1/3 in parentheses so that you know that both the top and the bottom of 1 and 3, like that whole fraction is to the x power. You could check this if you plug in any of those points, any of those x values, and you take 1/3 to that power times 12, you're going to get that y value. Yeah, what if we picked, what if we picked 2? I'll do that real quick. If I plugged 2 and 4/3 in there, I would get 4/3 equals 12 times b squared. You have to divide 12 over, and then how would you get rid of that b squared? You had to square root both sides. And because we said that that b needs to be positive, you would take the positive root of that. And you can do that with any of them, really. But what if it was a negative? How could you get rid of that? Yeah. Oh, that's not 4/3 anymore. If it was -1, you would get 36 equals 12 times b to the -1. And you'd get 36 equals 12 over b. How could I solve that? I could multiply both sides times b, and I'd get 36b equals 12. Oh yeah, it is right, because it's a little tricky though. When you solve this, yeah, you divide by 36, and you still get 1/3. Right, you still get the same answer, no matter which one you do, but it's definitely easier to pick one if it's there. But you should have the skills to solve any of those, right? But you only need to do one. Okay. The other big thing I want to look at today is graphing these. And again, this isn't so bad to graph. Logarithms, a little more work to graph. But I think as we go through this, you're going to realize, oh yeah, I remember this. It wasn't so bad. We're only doing exponential today. Logarithms aren't for a little while longer. Where's my... Why even try to do this anymore? Because it always squishes this way. Okay. I want to graph a few of these, and you probably saw them already, but I want to graph these so we can kind of see what happens when we graph these, what are the common characteristics that exponential graphs are always going to look like. And so I'm just going to start with an XY chart. And I'm going to pick a few points on this first one, and then we'll see that maybe we don't have to pick so many the next time. If I plug in 0 there, what am I going to get? 1. Anything to the 0 power is 1. If I plug in 1 there, I'm going to get 2 to the 1, which is just 2. And if I plug in 2, 2 squared is 4. And it's getting bigger and bigger. As x gets bigger, y is getting bigger by a power of 2. Do you agree with that? If I plug in 3, I would get 8. 4, I would get 16. It goes up very quickly. That's why we say it grows exponentially. What happens if I plug negative numbers in? Like -1. 1/2, right? -1 would be 2 to the -1. You move it to the bottom, so that's 1/2. Yeah, whatever has a negative exponent that goes to the bottom. And then you take the power. So what if I did negative 2, Logan? Well, what would 2 to the negative 2 be? What do you do with the negative exponent? And then what happens to the negative exponent? So do you get 1 over 2 squared? Which is 1/4. Am I ever going to get 0 on that y column? What if I plugged in negative 100? I get 1 over 2 to the 100th power, which is that 0? It's really small, but it's not 0. So as we graph these, there's some, like, hopefully you're going to realize that there's this nice pattern here that's happening. My graph's really small, but 0, 1, that's my y-intercept. 1, 2, 2, 4. I'm going to go ahead and say 3, 8. And then as I go back, I'm going to keep getting smaller and smaller. I'm going to get 1/2, 1/4, 1/8, 1/16. And it's going to keep getting really, really small, but it's never actually going to give me a y value of 0. Is there any exponent I could ever plug in that would give me a negative value there? No, I'm never going to get a 0. I'm never going to get a negative number. So I think that means we have an asymptote going on here. This side's going to go up, and this side's going to come back and never quite get to that x-axis there. Every exponential graph will look something like that. Just there could be transformations. So you try this one. Graph 3 of x. You should see a very similar thing going on, except for now it's a power of 3 instead of a power of 2. When you plug in negatives, you get fractions. When you plug in positive numbers, they just keep getting bigger and bigger. Bigger than the 2s a lot faster because it's a power of 3 now. But you should also notice again, we're not getting 0, we're not getting negative numbers out of this. It should look something like that. It should definitely be a smooth curve. It should not be like jagged. Notice the y-intercepts are the same. When we plug 0 in there, we always get 1 out of that, unless there was something else multiplied by it. And so those are very similar to each other. What if we graphed 2 to the negative x? What happens when I plug 0 into 2 to the negative x? I still get 1, so that y-intercept hasn't changed. But what happens now when I plug in positive numbers? What happens if I plug in positive 1 into 2 to the negative x? Yeah, when I plug in positive 1, I'm going to get 2 to the negative 1. So now I'm going to get fractions on that side, right? If I plug in positive 2, I'm going to get 1/4. What happens when I plug in negative numbers? Yeah, because if I plug in a negative up there and it's already a negative x, that's just going to become 2 to the first. And if I plug in -2, that's going to give me a +4. So it's important to notice there that that negative is going to flip our graph. Now the negative side is getting bigger and the positive side is getting smaller. We're still not getting 0. We're still not getting negative numbers here. But now -1 gives me 2. -2 gives me 4. And I get those fractions on the other side. So it's flipped over the y-axis. If you think about our transformations, a negative up here in the graph or in the function does always flip it over. But hopefully with exponential functions, maybe you remember something about exponential growth and exponential decay of something getting bigger or smaller over time. That's kind of the difference here. The next page here, I just wrote some characteristics. The difference between when we have a positive exponent and a negative exponent in our exponential graphs, and some characteristics that are always true. That means when you make your graphs, these things should always be true. So let's look at that real quick. And I kind of just separated them. I have what happens if you have an exponential function, y equals a to the x, where your base is a positive number and your exponent is a positive number, as opposed to what happens if you change that to a negative. Some things aren't going to change. Look back at those graphs you just made and tell me what the domain of all of those graphs are. It's the same for all 3 of them. What are the x values you're allowed to plug in there? Yeah, and if we go back, I don't know how small this is going to make this if I double page this. But on all 3 of these, we only picked nice numbers here. But look at this graph. It's going to go forever this way on the x-axis. This side's going to go forever. You could plug in fractions for x. You could plug in decimals for x. You could plug in negative numbers. You can plug in positive numbers, which means the domain of every exponential function is always going to be all real numbers. I'm going to say -infinity to infinity. What? Some things are going to change. The domain and range, like I said, some things aren't going to change. I have a whole bunch of stuff here, though, that we're going to talk about. I was just doing domain and range first. What about the range on all of these? I think Logan was looking ahead here. And do you agree the range on both negative exponents and positive exponents, I'm going to have the same range? What am I never going to get for the y values? Negative, and what else am I never going to get? 0. So you can write this a couple ways. Interval notation, I'm going to say I'm going to start at 0, but not include 0, and go to infinity, which is the same thing for this one. Or you can say, if you're a set notation kind of person, y's such that, what? What could you say? Yeah, all positive numbers would work also. I would just write the inequality. Y is greater than 0, not including 0. And again, both of those are acceptable. I'm going to go back to a full page. What about the y-intercept on all these graphs here when it's just a to the x or a to the negative x? And what's it always going to be? Yeah, because when you plug 0 in, you just get 1. Here's the big difference here. They're both continuous functions. They don't have any breaks. They don't have any gaps. But if it's a positive exponent, it's going to be an increasing function. Like it's going to be going up. We call that exponential growth. But if it's a negative exponent, that graph's always going to be decreasing, which means as x gets bigger, y gets smaller. And every single time we had our range stopped at 0, it didn't even include 0, which means that we have a horizontal asymptote. Exponential functions do not follow the rules of horizontal asymptotes for polynomials. You have to just remember that you can never get 0 out of that no matter what you do. So these will always have a horizontal asymptote, and if there's no transformation going on, that will always be at y equals 0. Every graph has transformations, right? I'm not going to just give you graph 5 to the x. That's not fun, right? We're about to. The rules of transformations apply to every type of function, which means on your homework tonight, you're not going to just be graphing a number to a power. There's going to be adding and subtracting and all the stuff that goes with it. And if you remember the transformation rules, it's really easy to graph them if you know what the graph looks like. If you don't remember them, you just have to make an XY chart. Everyone okay? Is everyone done with this? So let's look at transformations here. I'm going to start with 2 to the x. I know we graphed it already, but I want to graph a few transformations of it to kind of show you, remind you of what's happening, which means I'm not going to make an XY chart for any of these. But I'm just going to regraph 2 to the x really quick, which means I know every time it has a y-intercept of 1. When I plug 1 in, I get 2. I plug 2 in, I get 4. 8, 1/2, and this side goes up, and this side, that should be going down a little bit, but that is my f of x equals 2 to the x. If you have all those rules we wrote out, I think it was in chapter 1 we wrote them out. You can go back and look at them. I'm not going to rewrite them for you. I'm just going to give you a few examples and remind you of what we can do with them. We already did an example of what happens if there's a negative up there in the x part. It reflected over the y-axis. Do you remember what happens if there's a negative out in front of the function, what that does? Flips it over the x-axis. So this is a reflection in the x-axis, which means you could just make an xy chart, but if you know that and you see that, you're just going to take that exact graph that you know 2 to the x looks like, and you're just going to flip it over. Now, no matter what you plug in for x, because it's negative, all of your y values are going to be negative. So when you plug in 0, you actually get -1. When you plug in 1, yeah, that's what reflection does, which is why it's so nice if you know those rules. You don't have to do all that work of making an XY chart again. Notice the asymptote's still the same, but now it's the negative y values that are used, not the positive. That's my h of x. What about if I said graph 2 to the x plus 1? What does a number up here in the function, added or subtracted, what does that do to my graph? Shift which way? Up, added or subtracted up here is left or right. Remember that it's the opposite way that you would think it would be, right? Plus 1, you think it would move to the right one, but it actually means it moves to the left one. You have to remember it's the opposite of what you think. So this means it moves left 1. Again, if you forget that, you have an XY chart as your option there. But for me, that means I can take my graph and I'm going to just shift all my values left 1. And the easiest one to check to make sure you're doing it right is your y-intercept. Normally, when I plug in 0, I get 1 out of that. But what happens on this one? When I plug in 0, what do I get? 2, because it's all shifted over. So this one's shifted over to here. When you plug in -1, that's when you get 2 to the 0, which is 1. If you plug in 1, you're going to get 4. See how all these are moved over 1? This one's going to be moved over 1. Just shifted 1. So it looks very similar. It's just shifted over one. This is my G to the X. I should have done like a shift of 7 or something so you could see that a little bit more, but that's right. Last one of these. Just want to kind of go over the 4 basic shifts or transformations that we have. What happens if a number is added or subtracted outside of the function? It moves it up or down, and it's exactly what you would think. If it's plus 3, that means it's going to move up 3. This one's the one that I'm probably going to be the pickiest on when you graph, because if everything shifted up 3, that means your horizontal asymptote has also shifted up 3. So you got to make sure that you keep that in mind when you're graphing it. But that means when I plug in 0, I'm still going to get 1 here, but 1 plus 3 is 4. So I'm taking that and I'm moving it up 3. I'm adding 3 to all of those values. I'm going to add 3 to this one. 1, 2, 3. So when you plug 1 in, you actually get 5. Plug 2 in. 1, 2, 3. You get 7. When you plug negative 1 in, you get 3.5. And here's what I want you to think about. Normally the asymptote is 0 because there's nothing added or subtracted out here. Whatever this is will be your horizontal asymptote, which means you're never going to get values smaller than 3 now. So my asymptote should never, like my line should never cross this right here. So that's what I'm really looking for when I graph, when I'm grading these, is that you know, that should be a straight line there, that that's where your asymptote is. You're not going to dip that all the way down and not pay attention that you think your asymptote's still at 0. That's kind of a big mess all in one graph, but hopefully that reminded you of those things. Last thing I want to talk about, the number E, which is again something we talked about last year. There's a lovely button on your calculator. E and LN, lots of applications, so we're going to be using them a lot. I think the big thing today is you're going to be practicing using your calculator with E. But just to remind you what E is, in case you forget, E is the forgotten irrational number. Everyone knows pi, but it is a number just like pi. If you type on your calculator E to the first power, it should give you that approximation, 2.718281828. I don't expect that you memorize that, but that's what E equals. And like I said, there's lots of applications with E, and we'll do a lot of them. And so just E is the number, just like 2. We can graph 2 to the x. We can also graph e to the x. And so that's a very special function. We call that the natural exponential function. Leonard Euler there, looks like Euler, like I say Euler. He's responsible for E, discovering E, proving what E is. I always say that's why we call it E for his name, but I really don't know. I just make that up. But you could graph this just like 2 to the x. You could use your calculator, and you could plug in E squared and E to the third. You're just going to get decimals, but you could graph it. Some people always ask me, what does E equal? Like, to find pi, you can take any circle's circumference divided by its diameter. You don't only have to write this down, but in case you're wondering where E comes from, if you take the sum of these numbers, 1 plus 1 over 1 factorial plus 1 over 2 factorial, and you keep going forever, that's where that number comes from. Remember what factorial means? Yeah, so the higher you get there, the smaller that number is, so that's why you can get such an accurate estimate there. Euler's a pretty old guy, and he gave the approximation to E correctly to 18 decimals, and that was way before computers and calculators, which is pretty impressive. Again, that's not really that important, but sometimes people always ask me that, so I like to throw it in there. All you're doing on your homework today is practicing getting some numbers, like with your calculator. Maybe graphing. We'll see. I don't remember. Here we go. These are my last examples. Again, calculator is definitely necessary for some of these problems. If you do not have a calculator, if you have a cell phone or a computer, then you have a calculator. And if you need
What's that scientific calculator app on your iPhone?
that's a graphic calculator app. Graph Calc Pro or something like that. Yep. You can pay 99 cents to get the upgraded version, but the free one has everything you need. If I said do this, that just means I'm going to take e squared. I don't expect that you take that decimal and you square it. I just want you to practice using your calculator because we're going to need that as we go later. On my calculators, it's the third one down, but you have to hit second. Like there's LN and then E is right above it. And I think we're going to go to 3 decimal places. The book will tell you what to round to. 3, 8, 9, I think. If you were graphing that, you would want to just estimate that decimal. And if I put -3 in there, should make sense to you that this should be a small number because negative means reciprocal, so it's going to be on the bottom now. I think we would have a 0.0. If we're rounding to 3 decimal places, do you agree that would be 50? Again, I recommend start bringing a calculator if you have one because we'll be using it a lot. Grab one up here in class if you don't have one so you can use it, and make sure that you leave it in here because we do need enough for everyone to have. So this is your assignment. And the bell's on screen, so I'm trying to hurry it up and pass it out. Your homework is 3-1 day 1, 1 through 13 odd, and then 15 through 30 multiples of 3 and 39. There's definitely some graphing ones on there. Try those, and then we'll talk about some of these applications tomorrow.